Welcome to this biochemistry lecture on protein identification. So the first topic we're going to talk about is an SDS page gel. SDS is a detergent. If you look over here on the right, you can see that when we take a protein sample, any protein sample, we put it in SDS, it's going to denature the protein. You can see before we have a globular protein. Afterwards, SDS linearizes it and it gives it 2 negative charges per amino acid residue. And then we're going to take it and load it onto this polyacrylamide gel. That's what PAGE stands for, polyacrylamide gel electrophoresis. So that polyacrylamide is like taking it and it'll separate it out by charge. Now we have because the charge is affected by the mass, the number of residues, you can separate out proteins by their mass. And that's what you have here. So this protein is run across a voltage gradient, and what's going to happen is the faster proteins are going to travel farther, and the larger proteins are going to travel less. And then we stain this with something like Kamasi blue or silver stain, and you can then visualize what size your protein is based on the first lane. In the first lane we put markers, standard sized proteins, so we know exactly we can actually identify what the size is. We know what size all the markers have. Then we can say, oh, roughly the most expressed protein is that dark blue brand, about 25 kilodaltons. Very briefly, this is an exercise in protein purification, and you could tell that because the LP, S, and F lanes, that's where they produce the proteins, they initiate the proteins, and then the wash and the elution buffers where they try to purify them off the column. And you can see that the wash steps had a little bit of leakage, but the elution buffers, they eluted off in the first two steps. So that kind of gives you an idea. Again, SDS page gel is used. The sample can be very dirty, but the idea is to see if we have the protein in the sample we're looking for. And gel electrophoresis. Electrophoresis is basically separating by charge, and we're going to see this in other biomolecules. So the next type of protein identification is a Western blot. And basically what you do in a Western blot, it's very similar to a page gel in that you do separate it out. In fact, you run an SDS page gel, and then you take that gel, which is a polyacrylamide, and you transfer it onto something like a nitrocellulose membrane, some kind of membrane that the protein will stick to, and then you're going to take antibodies that are very specific to that protein, and they're going to have some kind of enzyme on them or some kind of label on them, and you're going to be able to visualize that label or the effect of the enzyme. And then off to the right is what you see. It's very, very clean because the antibodies generally are very specific. For the markers, generally we used to take the blots, and there was a dyed protein, and we could very easily just pencil in where the markers were, so we knew exactly where we were, and then there'd be a signal at where the protein is, and it looks very clean based on that sample. So the idea is we run an SDS page gel, we transfer it to a blot, we add an antibody, we wash away all the excess antibody, and then we visualize that either through some kind of enzyme or some kind of tag. And Western blots are very, very specific. They're not as sensitive, but they're very, very specific. And so they're very commonly also are very good at detecting linear epitopes, and sometimes the conformational epitopes are not as easily seen unless you run a native gel. A native page gel would not put SDS on there, so it won't denature the protein. That's a topic for a different day. But a Western blot is very, very specific, and it's one of the most fundamental ways that we identify proteins. Commonly, people try to get away with page gels, but frankly, a Western blot is where it's at if you need to identify your protein because of the high degree of specificity. So another type of gel electrophoresis is a 2D gel, and again, this is commonly we do very similar to what we do with a gel electrophoresis, an SDS page gel. The exception is that we would do a first dimension separation by PI. And PI, as you might recall, is the pH at which there is no net negative charge. And so we commonly will run a protein in a pH gradient, and then we'll take that column and we'll run and separate out the molecules by charge. And so what you have is a two-dimensional, meaning we have across the top, we have the proteins separated by their pi, and across the side, you have them separated by their mass. And that gives a very clean picture, because if you run an SDS page gel, if the protein is 500 kilodaltons, if you have two proteins that are 500 kilodaltons, there's no way to distinguish. Well, this gives you one way of distinguishing, as well as the others, which are your Western blots, which are highly specific. What you'd commonly do from this is you wouldn't know what protein. You'd run this in a situation where you didn't know your protein. If you're running a Western, you know exactly what protein you have, and you're trying to identify it with, you're trying to be very specific to the antibody. In a 2D gel, commonly you don't know what you're looking for, and so you are able to cut out that band and run mass spec or some other kind of protein identification technique on it, and that will give you the answer to your question. Another type of protein identification is an ELISA. And ELISA is very sensitive. It does have some degree of specificity, also dependent, but that's a little bit dependent upon the antibodies, but it's very, very sensitive commonly. So the way the theory goes is you put a capture, and an antibody is a molecule that binds to your target protein. So you have a protein, your favorite protein, called the target protein. You put inside a well of a 96 titer plate. You put in some of your capture antibody, and then you wash away the excess. You put in your target protein, which is step 2. Your target protein will bind to your capture antibody. It's on the surface. You wash your excess target protein away. Then you flow over a second antibody, commonly called the target antibody, or sometimes it's called a detection antibody, or sometimes it's called a secondary antibody. Commonly, this can have a TMB attached to it as well. In this situation, on this graphic, they have a biotinylated detection antibody or target antibody that is going to be attached to by a streptavidin that's conjugated to a horseradish peroxidase, which is what HRP stands for. So you take and you put horseradish peroxidase in this, a biotinylated or a streptavidin or an avidin tag on a HRP that is going to bind to a biotinylated antibody, and then you put your TMB substrate and the well-turned colors if there is a binding, if there is a complex. So you get a high degree, and this is very quick, of sensitivity, and it's very, very quick. There's a wash step in between every one of these. There are different types of ELISAs. You can do a direct ELISA where you take your antigen and put it on the bottom of a well, and then you take an antibody that has a conjugated HRP, and then you can just do two quick steps, actually 3 quick steps. You take your binding event, your primary antibody, and then a TMB, and you can get a signal. An indirect ELISA, commonly used when you're using serum. You put down your target antigen, you flow over a first antibody, a target antibody, and then you flow over a second antibody that binds to the first antibody that has an enzyme to it, and so then you get a signal, but still it's an indirect ELISA. A sandwich is what we described in the first video, and you can have a competitive ELISA where, and this is what I do mainly for a living, you can have an antibody that binds the same epitope, an epitope meaning on the target, it binds on the same spot. Proteins commonly bind, or antibodies commonly bind in the same spot. So competitive, you take 2 antibodies and see if they block each other. So those are the types of ELISAs. There's 4 general types, although there's very different variations, and you can find all kinds of people who will tell you different things about ELISAs. The last mechanism of protein identification that we're going to talk about is mass spectrometry. There are 4 major steps in mass spec, as we call it. There's an inlet, and you can have a solid, liquid, or a vapor. Commonly, we do liquids. You then ionize that, and that can happen in any number of ways that ionization is sent through some kind of mass analyzer. It's usually sorted by ions, by mass, and then that ion, there's an ion detection algorithm, and you get at the bottom you can see we get some kind of mass spectrum that allows you to identify the different proteins by their mass. So that's the general theory behind mass spec. So the general theory, there are dozens, if not hundreds, of mass specs out there, and there's three general components to every mass spec. There's an ion source, a mass analyzer, and a detector. And they can come in any different combinations. And things like the mass analyzer, you can put 2 in a row, and that gives you a more specific signal. Generally speaking, I don't spend a great deal of time talking about mass spectrometry, but just know that there's multiple different types. You can have, liquid, gas, electrospray, MALDI, and the list goes on and on and on. And the general idea is we're going to take and we're going to try to identify a molecule based on the size. And we're going to create an ion source, and so there is an associated mass to ion ratio, and then we get some kind of spectrum that allows us to identify what that molecule of interest is. Thanks for listening. Look forward to seeing you in the next video.